This webinar is sponsored by NEC Corporation, a $37 billion technology leader with a 100-year history of innovation. NEC's Programmable Flow Networking Suite was the first data center-grade SDN leveraging the OpenFlow protocol. Deployed globally today, Programmable Flow transforms network performance and agility by providing production-ready SDN solutions that increase flexibility, visibility, and efficiency while reducing complexity and costs.
To find additional SDN, OpenFlow, and network function virtualization resources, visit ipspace.net/SDN. The next topic I want to mention is network function virtualization, which appeared probably a year after the SDN and OpenFlow started to be heavily marketed. And it's really a very simple concept. It started with service providers who were sick and tired of buying dedicated network appliances. Because if you really look inside a network appliance, quite often, if the appliance is working at layer 4 or above, you will find x86 server inside the appliance box. There might be some ASIC glue. Some high-end vendors use dedicated hardware, for example, in firewalls. The brass termination might be also done in hardware. Some vendors have DPI devices that use hardware offload. But most mid-range appliances, you open them, there's Intel inside. This applies equally well to firewalls, to load balancers, SIP gateways, whatever termination, be it PPPoE or 624 tunnels or map gateways or DS Lite. DPI devices usually do most of their work in software because it's hard to do it in hardware. If you take a look into those appliances, it's just Intel server. Why can't we deploy the same software on a generic server hardware? What would we gain? The thing we would gain most is flexibility. Instead of buying dedicated appliances and not using them to their full capacity, we could buy a server farm and deploy smaller appliances as virtual machines on those servers. Or in large-scale environment, I could just deploy the same appliance on a bare metal machine and then, based on my traffic needs, switch the bare metal machine from one appliance to another. I would just need to boot it off a different disk. Once I decouple the software that was running on an Intel server anyway from the box in which it was packaged, I can start building scale-out architectures that are very flexible, that can meet the demand whenever the demand is there, and that allow me to do all sorts of interesting things that we could always do in the server virtualization world, but we couldn't do it in the network services world. For example, in every single data center, you have firewalls and you have load balancers. You usually implement application stack by taking different servers, grouping them in VLANs or what have you, and inserting network services between these zones or subnets or whatever you want to call them. Traditionally, these services would be implemented in network appliances. When you want to move the application stack from data center A to data center B, you can't do it because you can't move the appliance. You have to have a similar appliance already resident in the other data center. Next, the appliances are expensive, so you want to use them as much as possible. Instead of using one appliance per tenant and giving the appliance to the tenant and telling the tenant to go configure your appliance any way you wish, we are combining tens or hundreds of applications or virtual IP addresses or whatever the appliance is providing on one physical box. That one physical box, first, becomes impossible to manage. Second, becomes a hugely critical part of the infrastructure because if it goes down, you lose everything. And it's impossible to mirror in the other data center. particularly if you have active data centers where you already have something running on a similar appliance on the other data center. And when the first data center fails, you have to merge two complex configurations. Now imagine that you virtualize all the load balancers and the firewalls. Number one, disaster recovery becomes extremely simple because all the network services are just VMs like any other VM. So you just restart all your VMs, including the services VMs, in your other data center. You want to move the application to the cloud? No problem. You move the whole application stack, including the firewalls and the load balancers, into the cloud. You want to test the application? No problem. You can reproduce the same exact configuration using the same load balancing and firewalling product in your QA or UAT environment. And finally, you don't need one huge firewall for the whole data center. You might give each application team their own firewall. Obviously, whether that is feasible or not depends on how your organization is set up and what the security rules are. But things are made way easier, way more flexible, and with each tenant having his own appliance, virtual one obviously, you can also give the tenant all the control of that appliance. They can do whatever they wish. So self-service, self-provisioning is no longer a dream or a complex orchestration exercise. It becomes extremely simple. Here's a really good comment from Terry Slattery saying, it's also easy to do upgrades in an NFV environment. Because what you do is you clone a VM, you upgrade the software on the VM, you apply the old configuration to the same VM, you see if it works, and then you just shut down the old VM and start the new VM. And if it doesn't work, you can go back in a matter of seconds. So with the ability to clone things, to test things, to have multiple copies of the same thing, your life becomes as easy as the life of the server admins became when they figured out how to manage service in virtualized environments. On the service provider side, they want to have something similar, not for the individual application stacks, but for their users. Here is an example from Deutsche Telekom's TerraStream project. They decided to have an IPv6 only access network. They said IPv6 is the way to go. We are building a new network, so we will go with IPv6, but we will not go with dual stack because dual stack just increases complexity. We want to reduce the complexity. We will have IPv6 only access network, and that's it. For IPv4, we will build 4/6 tunnels. The implementation they use is somewhat specific. It's called lightweight 4/6. It's sort of a mixture between MAP and DS Lite, and they need something to terminate those tunnels. Guess what? They decided to implement that part in generic servers in their data centers. So they have a data center very close to their core routers. So every pair of core routers has a data center attached to them. In those data centers, they have server farms, and on those server farms, they run the VMs that provide the tunnel termination and IPv4 connectivity to the CPEs. Why would they do that? Number one, it's very easy to scale. You get more users, you start more VMs, you're done. Number two, they know that this is a transition period. They know that IPv4 traffic will start going down. And when they get rid of most of IPv4 traffic in the next 3 years, let's say, they will still have servers that will be usable. If they would implement this on dedicated appliances, then 3 years from now, they would have idle appliances sitting there and burning power. With the generic Intel servers, they will just repurpose the servers to do anything else. From their perspective, this is the ideal solution. Now, both use cases look like heavens on earth. You're old-time networkers, you know there must be a catch there. Catch number one is performance. Most of these appliances will give you approximately 3 to 4 gig per a Xeon CPU core. This is assuming they do something very light. Stateful firewall, simple load balancer, you get approximately 3 to 4 gig per CPU core. The limiting factor is number of packets processed. So usually they would do the test using something like iMix. They don't want to use small packets when doing these tests. Now, this is not what an Intel server can deliver. An Intel server can easily deliver more than 10 gig per a single core. And then based on the server architecture, the mid-range servers that are not optimized can deliver something like 40 gig. And the problem is not the CPU, the problem are the buses in the server. I've seen people who have been pushing more than 100 gig through an Intel server, but they knew what they were doing. So what's happening between 3 to 4 gig on one end and 100 gig on the other end? The first bottleneck is the TCP stack in the virtual machine. If you're using whatever software, be it open source or from a commercial vendor, that is using standard TCP stack, then you're limited to 3 to 4 gig per CPU core. The problem is that there is so much context switching between the kernel mode and the user mode and interrupt-driven processing and so on and so on. If you want to have higher performance, you have to get rid of the kernel, you have to get rid of the interrupts, and you have to do all packet processing straight in user mode, interacting directly with the hardware. For example, this is what the PF-Ring software for Linux does. Unfortunately, you can't interact directly with the hardware if you're running on a VM. And what you can do there is you can create virtual NICs out of the physical NICs with something like SRIOV, which is exactly the functionality you need. And then you use something like hypervisor bypass and you dedicate the virtual NICs straight to the VM. You do that, you can easily get 10 gig per core or more. If you want to use the hypervisor virtual switch, that becomes the next great bottleneck. Fortunately, there are people who know what they're doing. Intel even developed a data path development kit together with a small French company that allows you to very quickly optimize your packet forwarding paths and get way more than the initial performance at the beginning of this slide. For example, NEC already did that and implemented a virtual switch with DPDK, and that switch fares way better than a traditional OpenFlow switch that you can get from some open source means. Finally, most appliances working on application layer work with TCP. If you're smart enough, then you can present TCP offload to those virtual machines and pass TCP offload requests down to the physical NIC. Now, what is TCP offload? It's very simple. Instead of sending 1500 byte packets to the interface card and out, the TCP stack is sending like 1 meg long segment to the interface card, and then that segment is sliced into individual packets by the interface card. If you're using TCP offload, it's very easy to push 10 gig out of a regular Linux VM. I did some tests, and within the hypervisor, I could easily get 20 gig between two standard Linux boxes running TCP offload, obviously. The problem is that TCP offload today only works with VLANs. So the moment you start doing anything else like VXLAN or NVGRE, you lose TCP offload, you lose the performance. This is, by the way, where the beauty of NEC's end-to-end approach comes back, because You could, with NEC's programmable flow switches, make VLANs locally significant. So you can use VLANs with TCP offload on the VMs, and then on the top of rack switch, which has to be an NEC programmable flow switch, you can map those VLANs into virtual tenant networks, and you don't even have to use the same VLAN number on every port of a virtual tenant network. A number of other problems that I have to mention. Don't think that network function virtualization is a done deal, particularly in service provider environments. You want to apply a number of services to the same user stream. Traditionally, you would have this magic appliance that would do everything. And once you start doing network function virtualization, obviously you want to decompose them. You don't know whether all functions will be used by all users. So to scale out, you want to decompose that. Second, managing virtual machines in a scale-out environment by hand doesn't work. We need automation. We need automation on provisioning. We need configuration automation. We need monitoring automation. It's a solved problem. Server people have solved it. We just have to apply the tools that they already developed to our networking services servers. Next is auto-scaling. As the load increases, ideally something would spin up additional instances of the NFV, whatever it is. High availability. If you're lucky and your services are stateless, like in Deutsche Telekom case, they have to configure the mapping between IPv4 addresses and IPv6 endpoints, but the service itself is stateless. So in their case, high availability is trivial. Any NFV VM can receive the packet and process it. Autoscaling is trivial in their case. They just spin up more VMs with the same IPv6 destination address they're using anycasting, and it all works. For stateful services, obviously things get way more complex. You need service insertion, you need service chaining, you need tight integration with orchestration and provisioning systems. In the data center environment, there are environments like VMware NSX, for example, when you get most of these things already integrated in working. There are obviously commercial cloud providers like Amazon that have solved this problem internally, only you can't buy their solution. And the last major problem on the technical perspective is that we don't have a standard API. So yet again, in the cloud environment, there are at least two APIs that are becoming standard, the OpenStack API and the Amazon API. In the service provider environment, I'm not aware of any standardized API that NFV vendors could use to offer their services in a standard format. And finally, as at least one of the attendees already mentioned, there are the licensing challenges. The appliance vendors simply haven't realized that times have changed. They love to license boxes. The only two vendors that I'm aware of that went beyond that are F5 with line rate system solution, and I think Embrain also has some bandwidth-based licensing. Most others are still selling you licenses for individual instances, be it physical or virtual machines. Here is a very good comment saying Cisco ASA is also licensed on bandwidth. I totally agree with you. So let me rephrase the previous remark. There are several vendors, Cisco included, but also I think F5 and A10 and probably a few others that give you a VM, and then there are licensing tiers for that VM where, for example, you pay X for 100 meg, you pay Y for 1 gig, but still running the same software, and you pay Z for, let's say, 8 gig, but still running the same software on the same VM. What line rate system did was a totally different model. They said, we will charge this much for 1 gig, and we don't care how many VM instances you run. And that's what I had in mind previously.
Thank you for attending this webinar sponsored by NEC Corporation. For more information on NEC or the Programmable Flow Networking Suite, visit us online at necam.com/SDN. To arrange a demo or to pilot Programmable Flow SDN, call your NEC account rep or contact NEC directly at necam.com/contact us. Thank you for your interest in NEC's Programmable Flow Networking Suite.
Additional SDN, OpenFlow, and network function virtualization webinars, recordings, and workshops, as well as other resources like books and case studies, are waiting for you at ipspace.net/SDN.